Okay, magnetic properties part 2. I will remind you first what we did in the previous lecture. We observed that Maxwell's equations, because they are Lorentz invariant in special relativity, require the corresponding modification to the molecular Hamiltonian. And that modification was that we add the scalar potential times the charge of whatever particle is sitting in that potential, and to the momentum term we add the product of the magnetic vector potential and that same charge. And then we have the external field vector potential. We've got the vector potential of the dipole, and we have looked at and discussed in some detail the fact that there is this arbitrariness called the gauge, coming from the fact that the magnetic field, the observable quantity, is the curl of the vector potential, and the curl of a gradient is 0, and so this thing is defined up to a gradient. Then what we looked at was the way we define all of those magnetic properties. They were first and second derivatives of the molecular energy with respect to the external field, with respect to the magnetic moment of the nucleus, to the magnetic moment of the electron, and such like. And of course, we know now from the previous slide the expression for the Hamiltonian, and then this Hellman-Feynman theorem has demonstrated to us that the derivative of the energy with respect to that particular parameter is related to the derivative of the Hamiltonian with respect to the parameter. In particular, we have actually derived the first derivative, the Hellman-Feynman theorem proper, and it says, okay, if we want the energy of the ground state and its derivative with respect to alpha, then we need to differentiate the Hamiltonian with respect to that parameter and take the expectation value with the ground state. And this, of course, simplifies the problem radically, because in the giant molecular energy Hamiltonian, very few things would actually depend on any particular parameter. And so the expressions for dH, d alphas that we looked at in the previous lecture and will look at in today's lecture are actually fairly compact. And then we wanted also the second derivatives, and of course the second derivative with respect to two parameters is even simpler, but there is this unfortunate complication that we need to take a sum over all of the excitations that are present in the energy level structure and calculate these expectation values with the first derivative. Okay, so let us now take a look at all of those individual derivatives and their physical meaning, essentially a complete catalog of interactions that come in this context of computing magnetic properties. Now, the first two here, the electron-Zeeman interaction and the nuclear-Zeeman interaction, they are actually from the outside. They come from special relativity. If you take Dirac's equation, eliminate the negative energies from that, you do get what looks like the interaction between the spin of the electron or the nucleus. So the electrons here are numbered by I and K, and the nuclei I and J, and the nuclei by N and K. And you've got these two terms, so the Zeeman interaction of the electron and of the nucleus with the corresponding G factors and magnetons. Now, what we did yesterday was to find a few more terms in here, and one of the easiest ones to understand is the orbital Zeeman interaction. If you have orbital motion of an electron, well, that's the negative charge moving on a circular trajectory. Such a moving charge is a current loop. The current loop is a magnetic moment. The magnetic moment interacts with the magnetic field, and the charge is negative, so the minus here cancels with the minus that was there in the mu dot B energy expression. So that one is straightforward. Then, if we look at the susceptibility part we did in the previous lecture, if we take the second derivative, so with respect to that field and that field, we notice that there was a bunch of coordinate operators remaining in there, and we call that Langevin susceptibility. If we look closer at the electronic structure theory part of how the nuclear spin interacts with the magnetic field, then when we take that derivative, we will see again a different bunch of coordinate operators sitting between the nuclear spin operator and the magnetic field. So this is clearly a contribution to the nuclear shielding from the electronic structure, which would get integrated away the moment we take this expectation value. And so this is nuclear shielding by electrons, and this comes in the ground state part of our large expressions that we've had in the previous slide. Then, if we look at the derivative not with respect to the nucleus and the field, but the derivative with respect to the two nuclei, so the magnetic moment of this one and the magnetic moment of that one, then another big bunch of coordinate operators turns up, and this would contribute, clearly because it's the interaction between the two nuclear spins, to J-coupling eventually, as well as other things. So this is electron-mediated nuclear spin-spin interaction. Then there is the contact interaction between the nuclear magnetic moment and the electron magnetic moment that turns up when the electron is very close to the nucleus, and in a couple of slides time we will see exactly where this delta function is coming from. This is contact interaction corresponding to the electron more or less being inside the nucleus in the situation where we deal with nuclei properly. So nuclear electron contact interaction. Then, of course, they will have the straightforward classical physics terms, right? The electron magnetic moment at a distance will interact with the nuclear magnetic moment, and this is straight from the classical physics textbook. This is the nuclear electron dipolar interaction, just two dipoles at a distance. Likewise, of course, between the two electrons, exactly the same, except a different bunch of fundamental constants and two electrons here instead of two nuclei. And then special relativity, Mr. Dirac gives us four different spin orbit terms for the electrons and the nuclei. So firstly, a nucleus here can interact with the orbital angular momentum of the electron. So electron has orbital motion that creates a magnetic moment. That magnetic moment interacts with the nuclear magnetic moment. So we have interaction between nuclear spin and electron orbit. Then, of course, for electrons there are multiple kinds of things that can happen. Firstly, an electron spin can interact with its own orbit around the nucleus. This is what you'd conventionally call the spin-orbit coupling, and this is what comes out of Dirac's equation when we derive Pauli Hamiltonian in big relativistic quantum mechanics. But, of course, the electron can also interact with own orbit, but around an electron. Well, it's hard to imagine two negative charges orbiting each other, but of course in a confined molecule they inevitably do. There will be some magnetic moment associated with that motion, and so we must have this own orbit around an electron. And then, of course, an electron spin can interact with the orbit of another electron because it also can have a magnetic moment. So all of these multiple terms have to be added up, and all of them turn up in those derivatives which we calculate when we use the Hellman-Feynman theorem to get our magnetic interactions. When you will compute chemical shieldings, J-couplings and hyperfine couplings in your homework practicals, you will see Gaussian printing you lengthy reports partitioning the contributions to chemical shielding, to J-couplings, to g-tensor and so on into all of these terms. And so then take a look at this long list to see where they are physically coming from. Then two final terms that come up: electron-electron contact coupling, again the same close range contribution of the dipole-dipole interaction, and the electron shielding. If we've got the electron and the magnetic field, there's another bunch of coordinate operators here. Now, where does this delta function actually come from? This is called Fermi contact interaction, and that is something that they wouldn't tell you at school when you're discussing the point dipole interaction. Of course, when we are at the exact location of the dipole at the distance of 0, then there is a divergence in the rotor of the vector potential of the dipole. And we can actually work it out if we start looking at this expression. Triple product of 3 vectors, as you remember, gets opened up in vector calculus, and one of the terms will be the divergence of this quantity. But of course, this quantity itself is the gradient of 1 over r, as you can see if you've got some experience with differentiating things. And then, of course, the divergence of a gradient is the Laplacian, and the Laplacian of 1 over r has this well-known delta function in it. And so when we look at the field of a point magnetic dipole, there is this usual long-distance contribution that is just what we are used to for the dipole-dipole interaction, but there's also this contact contribution. And this interaction, eccentric as it may appear, actually dominates the hyperfine couplings between nuclei and electrons and dominates the J couplings in a lot of cases. So exotic as this looks, this is centrally important for a lot of magnetic properties. All right, so let's take a look at a few more places where all of these derivatives appear, and let us discuss the corresponding physical meaning. J coupling, the interaction between 2 nuclear magnetic dipoles. And if we look at the standard NMR textbooks, this is what we are going to see. Nuclear magnetic dipole A, nuclear magnetic dipole B, and a 3x3 matrix between them. Now, funnily enough, in a lot of chemistry textbooks, if you look at the J-coupling chapters, they will treat it as a number, so something without a directional dependence. In some textbooks, it's even explicitly called a scalar coupling, implying lack of directionality. However, in reality, of course, we have 3 components of the dipole here and 3 components here. So that's a 3x3 matrix. J-coupling is actually a tensor. It is anisotropic. It's just the anisotropy is so small that we really have difficulty detecting it even if we try. And in a liquid, rapid rotational motion of the molecule averages out the anisotropy, and so the only thing we are realistically seeing is the isotropic average of this, which is 1/3 of the trace. Still, certain electronic structure theory packages like ORCA will actually print you the full 3x3 J-coupling tensor. And as you can see, it's the second derivative of the energy with respect to the 2 magnetic moments. And now we pull all of those terms that we've just discussed in the previous slides and take a look at what turns up in there. So remember the Hellman-Feynman theorem. The second derivative only contains this electron-mediated nuclear spin-spin interaction. And this is one of those cases where this contribution, the contribution from the ground state to J couplings, is mostly actually negligible, as we will see when we take a look at a few examples in the next slides. The interaction is dominated by the electron nuclear contact term. For the 1 bond J couplings in CH&O molecules, so up to 80% of it is that term here. And if you look at 2 bond J couplings, 3 bond J coupling, at couplings across multiple bonds in aromatic systems, particularly for heavier elements, then this dipolar contribution and the spin orbit contribution also become important. So beware of heavy elements and conjugated bond systems. In those cases, you need high-level post-Hartree-Fock series like configuration interaction, and DFT actually begins to fail. But for 1 bond couplings, in a lot of cases, it's just the electron-nuclear contact and DFT, and even Hartree-Fock on occasion do work reasonably well. You would need a giant basis set though, so that's a paper by Frank Jensen where he painstakingly analyzed those 4 contributions that you've seen in the previous slide. So electron-mediated nuclear spin-spin is negligible, right? Just a few hertz, but still it only gets to its proper level in a triple zeta basis set. So something big is needed. In fact, polarized core as well, and polarization functions in the valence part as well. So these are giant basis sets. And that's just the F2, so Frank could actually afford to run these calculations. Then nuclear interaction with the orbit of the electrons, again, only converges at the triple zeta basis set level. And this is a significant contribution for fluorine because it is towards the heavier side of the second period. Then nuclear electron dipole, as you can see, only properly converges in the 4th click here, so quadruple zeta basis set. And the nuclear electron contact seriously depends on which basis set you choose. Right? If you don't have tight functions in the nuclear region, there's a very realistic chance of getting it wrong. So that is the Fermi contact contribution. And then he has summed all of that over, and that's the number of basis functions. So you've got all of these various basis sets. And then it slowly converges. So even for a diatomic molecule, right, fluorine in this case, you need, north of 200 basis functions in order to converge properly. And of course, if it's a big molecule, then this quickly becomes prohibitively expensive. And notice here that it's not actually the experimental value, it is modestly called the basis set limit, because as far as I know, nobody even knows what the experimental value for J-coupling is in fluorine, because, well, A, it is a serious pain to measure, and B, I don't think it's even possible to begin with, because the J-coupling between F19 and F19 is not going to be visible, but F18 is radioactive, and so even measuring it here is a bit of a problem. So you would need polarized core basis sets with large zeta numbers, and basis set convergence for J-couplings is very slow from here, and non-contact terms become significant. And this is why when we are writing our paper with Anu at the moment, when we wanted the J-couplings, we went and asked the experimentalists, because there's a 0 chance of getting this precisely right for the reasons that we will now discuss. Okay, so let's take a look at the performance and the contributions from those 4 terms at different levels of theory for different J-couplings in just, nitromethane. Something's really, not what's called cyanomethane, something very small. If you look at the Hartree-Fock, so the other name for that Hellman-Feynman theorem is coupled perturbed Hartree-Fock, CPHF, it's not even the right order of magnitude. Right, the experiment is not sensitive to sign, so it says plus minus, but a coupled cluster gets it pretty close. Again, for the CH coupling, likewise, for CN coupling, likewise, etc. Right? So these are really quite bad, and of course here once again there is no experimental value for the coupling between the protons, because all protons are equivalent in there and you simply don't see it. This is the comparison between DFT and second order polarization propagator. It's a particular method on top of coupled cluster. You can see DFT is seriously off, whereas the 2 SOPAs get it roughly right up to the sign, to which experiment is not sensitive. And for the 2 bond one, everything is reasonably okay. That is another comparison. That's the straightforward Hartree-Fock. That's the multi-reference Hartree-Focks of various kind, and that's the coupled cluster. Once again, you can see that you need to go to the coupled cluster level before you consistently reproduce all of the J-couplings, even in this tiny molecule that doesn't even have an aromatic system in it. And to add insult to injury, of course, because the J-coupling is often dominated by Fermi contact interaction. Fermi contact interaction propagates through orbital overlap, and the orbital overlap depends on molecular conformations. Right, this is the famous Karplus curve that is a significant chunk of Luke's project here. And when we rotate this dihedral angle, the bonding and anti-bonding orbitals of these CH bonds overlap to a different extent, the result being that depending on which conformation of this molecule you're looking at, the J-coupling can be anywhere between 0 and 15 Hertz. And in solution at room temperature, all of these conformations will be somehow populated by the corresponding energy, so Boltzmann law. And so we need to do the full conformational average to even have a chance at predicting what the experimental J-coupling has to be, and this is seriously difficult. We've done it in the past. Look at the past papers that my lab has published with Bruno Linklau. It is difficult, but it can be done, but the calculations quickly become expensive. So J-coupling, serious nightmare, humongous basis sets, coupled cluster, etc., on top of conformational averaging requirements. This is one of those properties which it is still, up to now, easier to measure than it is to reliably compute. Right, next item in the same class is the g-tensor, and that is the electron equivalent of chemical shielding. It's the interaction between the electron magnetic dipole moment and the applied magnetic field. And just as we had it for shielding, it is then the second derivative of the energy with respect to the electron magnetic moment and the magnetic field. When we take those Hamiltonian derivatives, take a look at what survives and write down the Hellman-Feynman theorem, we see the electron Zeeman, so that's the straight interaction that doesn't even depend on the on other electrons being there or not. Then that bunch of coordinate operators that correspond to this diamagnetic shielding, which we contract with the ground state. But then there are contributions from the spin-orbit coupling, and this is very serious because a lot of radicals that we are dealing with in practice, the unpaired electron in them does sit on something heavy or even sits on a metal. So D elements like chromium, iron, F elements like gadolinium, dysprosium, and so on, and occasionally even actinides these days, where all of that becomes seriously important. And the orbital Zeeman terms that we have here. Unfortunately, DFT is a recipe for disaster. If you look here, G parallel and G perpendicular refer to directions within the molecule, and you can see that compared to the experiment, this is molybdenum complex. Of course, it's consistently wrong because molybdenum is a D element where all sorts of hell breaks loose. I wouldn't even cover that in this lecture course at all. And in this case, once again, different exchange correlation functionals. Compared to the experiment, as you can see, some components are correct probably by accident, but then you've got the other two components, so x, x, y, y, and z, z, and the isotropic one certainly is way out. So if you are after calculating the g-tensor, either treat it as an order of magnitude estimate for the anisotropy that you are going to have, or talk to professional computational chemists who can do these things for you. That's another example of the strong effect of relativity as well. Typically, the more the G factor deviates from the free electron value, the more that spin-orbit coupling term is responsible for that. Spin-orbit coupling term that then implies heavy element. Heavy element implies then the relativity from which the spin-orbit coupling had originated to begin with. And as you can see, the things diverge from the predicted value, right? So it's calculation versus the experiment. So if you've got giant g shifts, then the entire derivative formalism is no longer applicable, because second and higher derivative terms become more and more significant, and we go into the territory, lanthanides, actinides, d elements, and so on, where the g-tensor itself as an approximation, as an entity, becomes a questionable approximation, because your energy levels are so mangled and so mixed between the magnetic effects and the electronic structure theory effects. So that's another example of straightforward small molecules, and as you can see, the calculations of the g shifts are nowhere near the experiment in a lot of the cases. So plainly speaking, if you are looking at a g-tensor, despair. Right? It is best measured, and it should not be computed unless you just want an order of magnitude estimate. Okay, but onwards to more optimistic things. That is the property that doesn't even require Hellman-Feynman theorem, because it's a ground state property. So nuclei with spin higher than 1/2 are not spherical. If you look at them, they're ellipsoidal shaped, they're sausage shaped, there are nuclei that are even heart shaped in some excited states, which means they've got non-spherical charge distributions inside the nucleus, which means that the nucleus has an electric quadrupole moment. Now, I haven't covered the theory of nuclear structure in this module, but it turns out that for nuclear ground state, the direction of the electric quadrupole is rigidly connected to the direction of the spin. And so any interaction that aligns the nuclear electric quadrupole would then necessarily also align the spin. And so this is how a purely electrical interaction becomes a spin interaction, because it just seems to be geometrically linked to it. So if we have a quadrupole moment of some charge distribution, there it is. So that's the charge distribution, and that's the quadrupole parameter, so the coordinate part. So you will have a 3×3 tensor called the quadrupolar interaction. The quadrupole moment, of the corresponding molecule, which interacts with then the electric field gradient. And of course, the electric field gradient, if we look at it, the electric field itself is the derivative of the electrostatic potential, and so the electric field gradient then is the second derivative of the electrostatic potential at the nucleus point. But that is a straightforward quantity to calculate. The only thing we need to know is the charge density of the molecule. We differentiate it twice at the nucleus point, and this is our potential second derivative. And then we have our V and U, and we contract them, and then this is the energy of the dipole in that electric field gradient. I will not bore you with the derivation of the corresponding spin operator. In fact, those of you who deal with catalysis and solid-state materials in magnetic resonance will have this derived to you in other courses, but essentially at the electronic structure theory level, we just need to know the ground state electron density. Through Poisson's equation, it determines the ground state potential. We differentiate the potential, and that gets us the spin Hamiltonian for the nuclear quadrupolar interaction. And because there are no excited states involved here, this is a straightforward calculation to do, except you do need to reproduce all of the electrostatics pretty well. So you still need a giant basis set, triple zeta with polarization functions, but the agreement with the experiment is quite brilliant. Now, there's a caveat here, is that this is not a perfect 45-degree line, and then the computational chemists are cheating somewhat by just fitting a straight line to what is to them an effective nuclear quadrupole moment, except, of course, that's a fundamental constant for a nucleus, but still, the straight line fit is pretty good, and you can have these calibration constants, which then get you the nuclear quadrupolar interaction, and that is the root mean square residual standard deviation in here and the corresponding fitting slope coefficient in here. And as you can see, as we go up the hierarchy of exchange correlation functionals, the electron density gets better and better. Therefore, the corresponding electrostatic properties get better, and the residual standard deviation improves. If you look at the corresponding improvement with respect to the basis set, it is a similar picture. If you take your standard triple zeta and start adding extra polarization functions, these polarization functions are in fact charge displacement from the nucleus, right? This allows the atom to be electrically non-symmetric, and the more you add, more or less, the better it gets at all levels. And likewise for if you start looking at specific atoms and adding specific functions to specific atoms, if you have polarized core augmented triple zeta, you get a pretty decent agreement with the experiment. So not a perfect 45%, it's the same as vibrational frequency. There's an empirical correction factor to do largely with, again, some non-Born-Oppenheimer effects and the finite nuclear size, but this is one of those quantities where if you deal with your molecule right in terms of the basis set and the level of description, it reasonably converges to a good experimental value. Then, of course, all other factors that affect the electrostatics need to be taken into account as well. If it's a crystalline material, you do need the periodic boundary condition and the complete crystal structure, because that is what determines the long-range electrostatics, and then that what is going to affect your electric field gradient. So in this case, this is anthracene from a crystal. And then there are various possible geometries for it here, and if you do it in vacuum, then none of them is close to the experimental value. But if you start doing it in a PCM, so in polarizable continuum, then one of the geometries gets pretty close. And then if you look at a dimer of anthracene to improve the description even further, then that same geometry number 2 is the best match to the experiment. And this is called NMR crystallography. In some quarters, you can run your electronic structure theory calculations until quadrupolar interaction parameters and to some extent chemical shifts match your experiment. And then it's a questionable claim to make, but they are still making it, that whichever structure has experimental like parameters is the one that is the true structure. Mean value theorem for vibrational and rotational and conformational averaging begs to differ, but at least in some cases that does work. Another table for you to hypnotize at leisure. This is external electrostatics. So QM/MM means you are treating the molecule quantum mechanically and its electrostatic environment at the molecular mechanics level. So just stick some tips 3p water around it to cap whatever should be capped with hydrogen bonds and things. And then the vacuum calculation is quite remote from the experimental value, likewise for the solution, but as you start adding better and better description to the molecule, the agreement eventually improves. And that's it for today. And that is it for the electronic structure theory. I have omitted a few particularly nasty magnetic properties like zero field splitting and exchange interaction, because they are a proper nightmare to understand as well as compute. But the things that you realistically will need in your daily practice in your various projects have been covered, and we start with quantum optimal control from the next lecture. Any questions?